All right, everyone. Welcome to the second Rice Wireless Distinguished Lecture. For those of you who are actually joining us for the first time, just a few instructions. So first of all, the talk is being recorded, and also if you have any questions, please feel free to leave them in the Q&A section down below this page. And at the end of the talk, I will just read them back to our speaker. You probably have, if you have enough time, you will have the chance to ask follow-up questions as well. Okay, so with that, let me start introducing our speaker today. It's our greatest pleasure and honor to have Professor Muriel Médard from MIT today. She is the Cecil H. Green Professor at the EECS Department of MIT, where she leads the Network Coding and Reliable Communication Group. Professor Médard has served as editor for many IEEE publications, including editor-in-chief of IEEE JSAC. She was also the president of IEEE Information Theory Society in 2012, and she served as on its board of governors for 11 years. Professor Médard has won many awards. I'm going to just mention a few latest. So 2018 ACM Sitcom Test of Time Award, 2017 Aaron Weiner Distinguished Service Award, 2017 IEEE Information Society Edwin Howard Armstrong Achievement Award, and many other best paper awards in IEEE journals and conferences. He is a member of the National Academy of Inventors and recently elected member of National Academy of Engineering for her contribution in network coding. She also recently received an honorary doctorate from TU Munich. So with that, I would like to welcome again Professor Médard. Professor Médard, it's all yours.
Thank you very much, Rahman, and thank you all for the invitation. I'm delighted to be able to join you remotely, and not as much as I would be in person, but I really appreciate you giving me this opportunity, and look forward to interacting with you in this way. So today's talk is going to be sort of a revisit of things I totally thought I knew, and I realized I didn't know the way I should. And these are some of the most basic, I would say, fundamental results of information theory, which I'm going to revisit from a different perspective with you in your company today. And then I hope convince you are not just elegant and interesting for their own sake, but actually open very new opportunities and quite exciting ones with respect to what we can do in communications. So it's about guessing random additive noise decoding, which we shorten for GRAND. This is work primarily with Ken Duffy. So all of this work has been with Ken Duffy, but also we have some other collaborators whom I mentioned. Okay, so just very quick principles of coding, because I know people have quite different backgrounds. What do we mean by coding? So this is what I call the Krebs cycle of data. You should be able to go around and around, except that of course there's some wastage at each of these links. So we start with data. We do what we call source coding. We compress it. We make a more succinct presentation. We then expand it, which may seem a little funny. Why did I compress it if then I'm going to expand it? But we expand it for the sake of becoming more robust, say to some errors or modifications that may occur in a channel, or what we mean by channel could be an actual physical channel, it could be a storage channel, variety of different effects that happen to the data, and that's really what we're going to concentrate on today. We then decode the source code, source decode, and keep going around and around that way. So there's quite a team here that I work with. I mentioned Ken, who's really the main co-conspirator in this work. But we have many other participants at MIT my student Amit Solomon, the student Wei An, whom Ken and I co-supervise, Anantha Shanakasan, who's the Dean of Engineering, 2 former postdocs of mine, Janjali and Kishori Kanwar, and Maynooth University, Kevin Galligan, who's a student of Ken, and at BU, our collaborators, Rabia Azizichigil, and two of her students. So why do we have all of these collaborations? Well, as you'll see, it's really because we're going all the way from theory to application. And what I'd like to do is give you here a little bit of a teaser. This is what we're going to see later, but this is a 5G new radio a standard CRC-aided Prolo code of the following length. So that means that you have 103 bits of payload, you send 128 bits of coded signals. That's the redundancy between the two, is basically what the code is giving you. In this case, it's 25 bits. This is with a state-of-the-art, what we call CRC-aided list decoder. This is with soft information, which I'll tell you later what soft information is. This is what we give, and this is what we could do with soft information. So just from the get-go, what I'm showing you is that immediately, even though we're going to start on the theory, if you're more an applications person, just hang with me, because we're going to show you really amazing results from the point of view of application. Okay. And in particular, we have incorporated this in a chip which just went out for tape out. So we have currently a chip that is doing this. We expect it back at the end of the summer, beginning of the fall, and stay tuned for more results. Okay. So let me start with channel coding just at the basic level, with all apologies to my very distinguished colleagues in the domain. But let's just think very simply what it is that we're doing. What does channel coding do, and why is it there? So suppose I give you a binary string, say 1 of 8 characters. I shout it, and basically one of them gets flipped. In this case, maybe the last one gets flipped. That's wrong. Okay, so how do we correct for that? Well, if any 8-bit messages were possible, then there's nothing we can do. You basically will receive this. It will say, well, that's a valid message. That's what she meant. So we have to agree, in order to be able to correct, we have to agree on a code book that's to be a subset of all 8-bit strings, so that when you see this, you at least with good probability say, I don't think that's what she meant, because that's not a valid code word. She must have meant something else that is in some way similar to what I received, but not quite what I received. So how am I going to, how are you and I going to agree on a code book so that when I transmit this and you receive that, with good likelihood, you're able to correct back to what I actually transmitted? And what Shannon told us is the following. There's a limit on how dense that code book can be. So we know that the code book cannot have a full density, say density of 1, where all 8-bit transmissions are possible, because then we're doomed. Obviously, I could have a density of 0. I could have only a single code word that's ever transmitted, but that's not very informative, so that we don't do that. So it's somewhere between 1 and 0, somewhere between having only one possibility and having all possibilities. That's what's going to give you the density. And he told us how dense code books can be while ensuring decode errors are rare. And we'll go more in detail what we mean by rare. And practical coding is the field, and it is a huge field, of the construction of these code books. Code books are computationally efficient for decoding. So we'll see later how we're going to basically remove that constraint. But basically what the code book does, it maps the received string to the element of the code book in a way which is simple enough. And the code book construction allows that simple mapping back. So how do we do things currently? Well, the engineering need is generally that we would like communication to be low delay, so we would need short codes, and we see that very much, for instance, in gaming, and a lot of the very difficult applications that are emerging in gaming and AR and VR. We would like it to be low complexity, of course. We'd like something that's very lightweight. We don't want to be spending a lot of energy decoding. for encoding, but particularly decoder is usually the more onerous part of the two. I would like codes that are very flexible. I'd like to have a lot of different rates, a lot of different block lengths. I'll show you later how current coding schemes are actually very inflexible. And finally, I'd really like to be robust to the physical reality of the correlated noise. With some of the conversations I was having with some colleagues ahead of this at Bryce, ahead of this presentation, we were talking about, how do you really take into account what's happening at the physical layer? Well, generally what we say is we don't really do that. What do? We tend to take these very long codes. And why do we take these long codes? Well, because the Shannon coding theorem basically was saying results that were happening at long lengths. Why? Because it was focusing on capacity, concentration onto correct decoding. Remember saying what I told you, I'll tell you what it means to have low probability of error, is that the low probability of error happens as the code gets very long, because basically you have, what we now, which maybe wasn't as understood in the engineering side, a concentration to the mean results in the 40s when Shannon was working, but we understand now show up all the time, this concentration to the means. It's this focus on capacity at long lengths. So the code constructions are really considering this focus on capacity. And because there are a lot of constraints around the decoding complexity, as I've mentioned, as I will illustrate later, the code constructions tend to be quite constrained in length and in rate. And so basically what happens is we have code-specific decoders that are married to particular encoders. So for instance, if I read Mueller code, I'll use majority logic. If I have a read Salmon code, I'll use Burley-Camp mask-safe. If I have a Polar code with soft information, without soft information, they don't work well, they don't perform well. I'll use, say, a CRC-aided list decoder. If I have low density parity code, I'll use belief propagation. And so there's a very tight co-design between the code and the decoder. One code may have several decoders, but you can't just take any old decoder and apply it to an encoder, right? That's not the way it works. Okay, so the current solution, by and large, as I mentioned, is to make the engineering look like the math. And what do I mean by that? What I mean is that, most practical, say, terrestrial wireless channels have bit error probability. So probably one of those bits flips. Remember how I showed you that my 0 flipped to a 1? The probability of that is like 10 to the minus 2, 10 to the minus 4. Really, let's say 10 to the minus 3, but more towards the 10 to the minus 4 range. Which means that the channel capacity, I'll show you later what the channel capacity is actually 0.92, 0.999. That channel capacity is the density that I mentioned before relative to how dense my codebook can be. Okay, so remember, channel density of 1 meant that any code word was possible. So 0.999 means not every code word was possible, but I'm eliminating very, very few code words out of my codebook. If instead you look at what we have right now in, say, some of the more recent standards, so the 3GPP, which is what does the cellular telephony, my phone, 5th generation new radio data channel, you're looking at codes that are super, super long and with really low rates that are really far below this capacity, okay? And moreover, I'm really not taking into account the physical reality of the correlated noise. What I do is I may measure the channel, but then I give up that information because I interleave in order to make the channel appear IID, that's to say independent, identically distributed. I want to make any statistical knowledge that I have about the channel, by and large, I'm going to forego, I'm going to break it up so that I make the engineering look like the math, because the math was developed for this IID model. Okay, now the new vision that we have is don't do this. Instead, focus on the engineering need and make the math look like the engineering rather than the engineering look like the math. And what does the engineering need? Low latency. It's not about capacity, it's about the highest rate available at short block lengths, whatever that may be. It's about flexibility. Okay, and we'll see later how inflexible current codes are. And it's not to fight the noise correlation. Is if there's any noise correlation, any information about the noise, use it. Okay, use it. Don't give it up by interleaving. I won't go much into detail in this talk, but I'm happy to talk offline with people about some of the recent results we have in that domain. So as I said, we're going to make the math look like the engineering. All right. What does that mean? What does theory tell us actually about short codes? If I tell you I want short codes, and if I tell you that Shannon was looking at these super long codes, and that many of the codes that are being used right now are super long, thousands and thousands of bits, and in effect longer, because if you take into account the effect of the interleaver, which itself may be over hundreds of bits, you're actually talking effect over 100,000 bits or more. Okay, so really, really long codes when you take both the coding and the interleaver into account jointly. Okay, here's the bit flip probability of 10 to the minus 2. So on the high side, given the range I gave you, here's 10 to the minus 3. And I have a target blur. Blur stands for block error rate, so the probability that a code word is wrong. And this is for different code lengths. Now, these are some nice results that are available on GitHub that have been pulled together by my colleague Yuri Polyansky. And what you see here is actual capacity. So this is what would happen at very long lengths. And eventually, if we went long enough here on this code length, which is the abscissa, you would get to capacity. This is the rate. So as I mentioned, one would be, full density. This is capacity, because you can still get very close to one, but not quite to one. And these are two achievability results, which are purely theoretical. I'm not going to go into what they are, but they're basically just proof techniques and not constructive. They don't give you a way of constructing the code and a way of decoding that code. What you can see is that somehow I'm not going to do better than this. Clearly, this is just an artifact of the math. Clearly, it's going to be here below, right? It's going to be the inner envelope of this. And so one of the things that you notice right away is that I shouldn't be worrying so much about capacity if I'm going at short lengths. I should be worrying about this converse and how close to that converse I can get. Okay. But actually, I should be worried about a whole lot more. And what do I mean by that? Well, if I use a structured code, I don't have a lot of choices. I don't have a lot of choices for my length. I may not have a lot of choices for my rate here. If you look at this heat map, I'm going from lower rate to higher rate, which also means I'm going from lower block error to higher block error, higher blur. So if I use a Reed-Muller, these are my only choices. If I use a Reed-Solomon, I have a lot of rate choices, but I only have a few length choices. If I'm using the 3GPP 5GNR, these are my only choices. Note that here one of the issues is that the standard actually adds this CRC, this cyclic redundancy check, so these extra checking bits, which affect my rate. So here I say, hey, pick any code length. This is what the math tells you can do. But actually, if you look at practical code, they don't look anything like that. And if instead you go and you do puncturing, which literally means making holes in the code, you actually lose rate. It's very inefficient, and it's a very ad hoc approach. It's never quite sure what you're going to get. So what does our approach give you? I'll show you later how to get this. But if I had a universal decoder and I didn't have to restrict myself to those codes that I showed you before, those, venerable structured codes, what you would see is that actually I can get all of these rates. And I'll show you later, that's why it's question mark. I'll show you later that I can do these rates, which are better than the theoretically best constructions. And again, theoretically, that means up until now, there was no way of obtaining that, but now we can. I'll show you how to. And you can see that they're very, very close to the converse. Again, remember the converse should, if you took the inner envelope, would really look like that. So we're basically at the best that we can do. Not capacity, because it doesn't matter. I can't get to that at this length, but really the truly optimal performance. Okay, let's go back to Shannon before I tell you how we're going to get those purple dots that nobody could get before. So I told you that Shannon told me how dense my codebook could be. How do we look at this density? It's this rate R. So if 2 to the n possible strings, remember in the example I gave you, n was 8, I have a codebook of 2 to the n R. So If R was 1, I'd be back to the n. R being less than 1 means that it's not fully dense. And what Shannon said is my rate is has to be less than 1, which would be full density, minus h, where h is the Shannon entropy of the noise. Okay, so basically what it means is I lose the amount that I need to represent the noise back. Okay, I lose the noise. I would have 1 R equal 1 if there was no noise, but I lose h of the noise. Remember when I showed you at the beginning the source coding and the channel coding? What that source coding does, the squishing down the information to its minimum, what the source coding does here, this source coding, this is where I get h. So this representation of the data, the minimum representation of the data that's really going to allow me to recover the data is h. So that's what the channel coding is doing. It's saying you can have everything you want except that which is needed to represent the noise. Okay? So how does he get to this? He says, okay, take my n to be large. I'm going to create a random code book. The way I'm going to do a random code book is I'm going to take my 2 to the nr, which is the cardinality, the size of my code book. I'm going to sprinkle them randomly among all the possible 2 to the n strings. By the way, randomly, uniformly, with replacement, okay? Just totally dumb. Just throw them around into these 2 to the n bins, okay? And that's how I make my code book, by throwing things around into these bins. That's how I make my code book. Okay, so I throw 1, then I throw another 1, and then I throw another 1, and then once I have 2 to the nr, I stop. Now, what happens is this code word was sent, and instead I receive a different string, which in this case was not one of the gray strings, was not one of the code words that I had chosen. And the decoding idea that Shannon had is, well, use the maximum likelihood. It's actually maximum posteriori, but it turns out to be the maximum likelihood because all the input messages have the same probability. That's part of the effect, remember, that Krebs cycle of data, is that post-source coding, post doing the compression, pretty much everybody has the same probability. And therefore, I can assume all my messages have the same probability. So we talk about ML, it's actually maxima posteriori, but they happen to be the same in this case, as I said, because basically all code words are equally likely a priori. And he said, well, look at the output that you got, which we're going to call Y, okay? And then take the argmax over all the code words in your code book, take the argmax of those, and that's going to be your maximum likelihood decoding. All right? Okay, done. So why are we doing this? Why aren't we just creating these random code words and doing what Shannon told us, at the middle of the last century? Well, here's the reason. If n is long, remember I showed you some sample code lengths of, thousands of bits, but let's say it's 1,024 bits, and R is large. Remember, I'd like to be at large rate. That means I'm sending more data. Then 2 to the nr is pretty darn big. I can't store these many strings. I can't do this computation these many times. It's not going to happen. Okay, so basically that's it. That's why it's a proof technique, and it was considered, these random codes, really just to be a proof technique. So out of the difficulty of doing the decoding that Shannon told us about, basically was born this huge coding industry with block codes like Reed-Solomon codes, which I mentioned before, convolutional codes, which are kind of like block codes. They're algebraic, except you're working with polynomials rather than just working over numbers. So-called modern codes that include low density parity check codes, which I mentioned before. I put them in between quotation. I put them in quotes because LDPCs date from the 60s. They were rediscovered, say, at the end of the 90s, beginning of 2000s. Turbo codes came in the 90s. Rateless codes, where you don't decide a priori your mapping, you don't decide on your R, the R just happens. Network codes, where you're not coding end-to-end, but you're coding, you can code in fact throughout the entire network, which has been one of my major areas of research. Polar codes, which Erica developed in 2009, which are actually right now, with that important modification of the CRC, of the extra check bits, in the 5G new radio standard, which I mentioned before. Okay, so here's my evolution of codes. There's still a lot of evolution of decoding. I mentioned the list decoding with CRC. That was, a few people have worked on it, but particularly Tom and Vardy, and it's recently been licensed by Samsung from San Diego. So a lot of activity, basically all centered around the fact that maximum likelihood decoding is too difficult. Okay. So we're going to do something that's going to look a priori insane. We're going to go back to a problem that we thought we knew since the 1940s to be super hard, and we're going to revisit it. Okay. Why do that? Welcome to the joys of tenure. Okay, you can go ahead and do that. If it doesn't work, it doesn't work. All right. We're going to concentrate not on the code. We're going to concentrate on the noise. So remember that my rate was 1 minus h. Okay? When I have a high rate, 0.9, 0.99, the rate is high. And remember, I have 2 to the nr possibilities. But 2 to the nh might be pretty small. Okay? So if my code is, say, 100 bits long, and my bit flip probability is 10 to the minus 2, my h is roughly 10 to the minus 2. 2 times 100 times 10 to the minus 2 times 100 divided by 100 is 2 to the 1. Okay, so on the rate side, it's huge. 2 to the nr is huge, but 2 to the nrh is not huge. And that's basically what we're going to do. And we're going to show that this is going to give you maximum likelihood decoding. It's going to require less computation at higher code rates rather than more computation at higher code rates, like all the conventional codes out there. I can actually abandon after a while. If it looks like I've been spending too much time trying to figure out the noise, I can abandon and still be capacity achieving. And I'll show you a little bit of how this particularly does with small block sizes. Okay, so remember, back to Shannon. Random code construction, throw code words around out of all the possible 2 to the n. So all of these bins here represent all the 2 to the n. The gray ones represent the ones that I chose as code words. And what I do here to go between one and the other is I basically have to identify the true noise. The noise sent me from this, which was the actual transmitted one, to this, which was the received one. Okay, so if I see the received signal and I want to identify the original signal, it's the same thing as identifying the noise. Now what happens is that I might make an error because I might think that instead of this being sent, well, maybe that was sent. Okay, and if I think that this gray one was sent as opposed to this pink one, really what I'm doing is I'm saying I think a different noise occurred. I basically made a decision that a different noise occurred, where the noise is the difference between the brown and the gray. And I'm going to call that, and we credit Andrea Goldsmith for giving us the idea of this nomenclature, the code word difference noise. The difference with the noise that would correspond to the difference between these two code words. When am I going to make an error? I'm going to make an error if I think that this code word difference or this code word difference, or any other code word difference noise, was actually the true noise rather than this actual noise. How many code word differences noise are there? Well, there's 2 to the nr minus 1, let's say roughly 2 to the nr, and there's only one correct noise, the one that actually occurred over the channel, the one that actually took me from the pink to the brown. Okay, so there's 2 to the nr ones that would take me to the brown to one of the grays, one of the other possible code words. There's only one true noise that took me from the brown, that took me from the pink originally to the brown. Okay. All right. So maximum likelihood, the way we were all told by Shannon. Receive the transmitted code word plus the noise. compute the a posteriori probability, so do the map/ML, the maps to a posteriori / maximum likelihood. Compute this thing for each and every code word to the NR1. Maximum likelihood is the highest a posteriori probability. We call that out of 2n possible words, the codebooks to the NR, and this decoding is exponential and very exponential in the sense that R, you want it to be high, right? You're interested in high rates, so this 2 to the NR is going to be close to 2 to the N. Particularly if I make my N large, is going to be quite complex. So what have people tried to do? Well, people have done things like sequential decoding, which dates all the way back to the 50s and 60s. And what they did is they say, I receive the transmitted code word plus noise. So this is usually done looking at the kinds of convolutional codes that I mentioned in my swoosh of code evolution. These are one kind of code, which are polynomial codes. So basically, they basically think of them as being shift registers, in terms of the construction. And what they did is they computed a posteriori probability of all code words and rank ordered, but because they had a particular structure for the code, a tree structure, you basically, that a posteriori computation was easier. It was easier. And so what they would do is they would guess according to the a posteriori probability order. They would check whether the decoding was a transmitted code word, and if it was a transmitted code word. But they had an issue here because they were doing this guessing and checking, but you needed to have a particular structure for the code, okay? And the particular structure for the code meant the following, that you could do this easily up to a certain rate, which is known as the cutoff rate. I'll show you later the cutoff rate in action. And the cutoff rate was kind of abandoned in the 90s when turbo codes came around that I mentioned in my swoosh. And then, LDPCs were rediscovered because people said, well, who cares about the cutoff rate? I can actually get to capacity. But the cutoff rate was basically the point up until which you had, manageable complexity, and beyond the cutoff rate you had exponential complexity. And so for a long time this was, as a folk theorem, really the achievable rate. People say, oh yeah, I know this capacity, whatever, Shannon told us about it, but you can't really get to it. Cutoff rate is the best that you can do. And interestingly, it was Arakan, who later developed Polo codes, who started using this concept of guessing, which I'll talk about in a little bit, in order to show that indeed the cutoff rate was the highest rate up until which you could guess noise without becoming exponentially complex, exponentially in R and an R. And it was actually his work on that led him to start thinking about how could you increase the cutoff rate. There's a beautiful description of this in this article he wrote for a special issue that I ran on JSAC. And basically he said he started thinking about how to increase the cutoff rate. And because he was thinking about how to increase the cutoff rate, that's what led him to invent Polo codes, which are in effect an increase of this cutoff rate. What other kind of decoding are there? Well, there's things like nearest neighbor decoding. So remember the example that I gave you before where I sent those 8 bits and only one of them flipped? You know, the natural thing, you would say, well, which one is in some way closest to the one that I sent? So basically what would happen here is you would list the noise sequences in increasing Hamming weight order. So say the ones with the most ones, where one is flipping a bit. And you would say, I'm going to look at the ones that flip the fewest bits. That might work well. It might not work so well if you have a channel, for instance, that has bursts of noise. In that case, maybe you have no bits, but maybe you're more likely to have a burst of 3 or 4 bits rather than a single bit flip. So basically, any robustness that I mentioned before around the actual statistics of the noise are going to be really difficult to incorporate into this. So what does our algorithm do? It receives a transmitted code word plus noise, the Y we talked about before and we're going to revisit. It orders sequences in decreasing probability, okay? So the most likely sequence of noise effect to the least likely, where the most likely could be all zeros, and if we're using a Hamming weight, so, errors being less and less likely, you basically put in a Hamming-Weight order, but it could be anything else. Whatever your noise statistics tell you, you subtract the noise sequence, actually the effect, and if it's in the code book, you return that code book. So let me show you specifically what I mean by that. So as I mentioned to you before, I have the channel output, Y, is the input plus noise. I'm using this plus here because remember, like in the binary case, for instance, a plus was a bit flip. So this would be a plus over a Galois field of size 2. But it's basically just some noise that can invert. And that's why I'm talking in particular about the noise effect, not the noise itself. It could be just plain old additive, or it could just be some effect that's invertible. The standard decoder tries to identify xn using the structure of the codebook. It tries to identify xn over these 2 to the n possibilities. What we're going to do is we're going to try to identify the noise. Remember, the rate is 1 minus h, where h is the entropy of the noise. So I am describing the noise. For me to find out what the x was from y, means that I'm also finding the n. So why try to find the x by looking at the more complex side of the sum? Why not try to find the x by looking at the complement, at the less complex side, the one that has a smaller cardinality? 2 to the nh is quite small, okay, because h is low. So here's the algorithm in all its simple, gory beauty. Codeword membership test. Basically, you put in y. I keep checking one noise effect, one after the other in decreasing order, whatever that noise effect is. And as soon as I find the first element that's in the code book, I shout bingo and I'm done. This is for any decoder, any code. This is a decoder that's universal. I don't care what the code was. The code is just a membership check. The code, in effect, is only a hash. Okay, so forget everything you knew about coding. And, I misspent as much of my youth as many of you on coding. So I say without any glee, forget about it. It's just a hash. It's just to check, is this in it or not? Okay? And the complexity here is a function of the noise, not of the code rate. Guessing noise. What does that mean? So let me take the example we had at the beginning of the talk where I had this bit flipped. Suppose that I go here in Hamming-Weight. So I start with, the sequences with fewest noises, with fewest flips. Suppose that here I say, well, what if the noise was all zeros? I go, well, let me invert that effect, which here is subtraction. Is this a code word? No. Okay, that wasn't it. Let me try the next most likely. Let's say that, for instance, I think that noise is more likely to occur towards the end of the code word. Why? Because very often towards the beginning of your transmission, you just got done with all the acquisition of the timing and so on. You're doing pretty well. And then towards the end of the block, things start getting a little less clear, a little less clean. So that's where bad stuff is going to happen. So if I'm going to guess that something bad happened, it tends to be more towards the end. Okay, I subtract that. I basically invert that effect. Is that a code word? Yes. Okay, fantastic. This is what is now the maximum likelihood decoding. Okay? Why is it still maximum likelihood decoding? Again, y is x plus understood in the wider sense of the term, n, the noise. ML decoding was the argmax, as I told you before, since Shannon of, let me look at the output, let me look at everything in Cal-C. Here is my code book of length n. It's the argmax of this. The argmax of this is the argmax of the noise. It's the same thing because it's an invertible system. So nobody thinks of putting it this way because why the heck am I looking at the argmax of the noise? I'm trying to get rid of the noise, not know the noise. But knowing the noise is the only way of getting rid of it. Okay? And the way I'm going to do the maximum likelihood in Grant is I'm going to decode by guessing. I'm going to decode the most likely noise, then the second most likely noise, the third most likely noise, and so on until I get that the subtraction of the noise, the difference between the y and the noise is actually in the codebook. All right. So I told you about the code word difference noise. The core idea for the performance analysis is that I have a race, okay? I have a race between the true noise, the one that took me, remember, from my pink to my brown, and the code word difference noise, all the noises that took me from my pink to all of the grays, from my brown to all of the grays. So there's a difference between the actual noise, this is one of them, the true actual noise, and the 2 to the n r minus 1 incorrect output noises, these code word difference noises. If I have a random code book, the location of these code word difference noises is uniform, right? Because remember, I threw code words around uniformly, even with replacement, right? So basically, the difference between anything and a code word out of my random code book is uniform, ID, because they just were chosen uniformly. There's no structure there. So the error, as I told you, occurs at a minimum of this 2 to the n r uniforms, 2 to the n 1 minus, and the true noise, okay? So the expectation, what is the expectation until I guess to an error? Well, this 2 to the n r uniforms, okay? And I'm just guessing all of the possibilities. The expectation until I guess the first error is going to be 2 to the n 1 minus r, because I have 2 to the n possibilities. Okay, so that's the number of guesses until I guess the first code word difference noise. Okay, because it's 2 to the n r. So there's 2 to the n r of them, okay? And the probability that I guess any one is going as 2 to the minus n. So it's the ratio of 2 to the n r and 2 to the n. That's what's giving me 2 to the n 1 minus r. Okay, because I have a Bernoulli process where any guess at any point is 2 to the n, 2 to the minus n probability of being correct. So what is the probability that I'll guess one of them out of 2 to the nr? It's this. It's the inverse of this. It's the expected time until I guess one. So guessing these code word difference noises is very easy to analyze. The part that's more difficult to analyze is guessing the correct output. The correct output, okay, is the true noise. The true noise, that's where the real structure is. The true noise is not uniform ID. The true noise has a low entropy. If the true noise was uniform ID, H would be 1 and my rate would be 0. 1 minus H, which is the capacity, would be 0. So the only reason I have a capacity is because my true noise is not uniform. And my optimal querying order, trivially, is going to be guessing from the most likely to the least likely. So what does that mean? I have this guessing order, and this is something that goes back all the way to Massey in the mid-90s, where he was looking at guessing for a password. And his question was, if I'm trying to guess passwords, obviously I'm going to guess from the most likely to the least likely. How long until I finish guessing? And is that related to the Shannon entropy? It turns out it's not the Shannon entropy. It's related to the Renyi entropy of order 1/2. Okay, so let's look at this. Average guesses until error is 2 to the n 1 minus r, just by simple Bernoulli arguments. The average guesses to the actual noise, the average time it takes me, I know from Massey, is actually 2 to the n h 1/2. Now h 1/2 is greater than h. And by the way, this would say, well, I'm going to guess the actual noise before I guess the error, okay? If this, the average guess to the actual noise, is smaller than the average guesses till, I guess, the code word difference noise, which would seem to imply that r is less than 1 minus h 1/2. Now, remember how I told you about, cutoff rate, folk theorems, stuff in the 90s that then got forgotten. This 1 minus h 1/2, that's actually the cutoff rate. And this is smaller than capacity. So what's going on? Well, I know that everything I did should give me back Shannon's coding theorem. I'm using a maximum likelihood decoder. With a random code book, I should be able to decode not just to the cutoff rate, I should be able to decode to capacity. So what are we missing? Why am I looking here like I go back to the cutoff rate? Let me look at this heat map going from the number of guesses bit in each layer. So let me look here at a length 200. What happens is to guess the actual noise, sometimes it takes a long time, but it only takes a long time because sometimes the noise is really weird. So if you think, for instance, of password guessing, which was the original motivation for these guessing results, well, the reason why guessing passwords is hard is because sometimes you guess very quickly. There's a very likely password. And if you fall on an unlikely password, it takes you forever. Okay. So sometimes you guess quickly if something is very likely, and other times it takes you a long, long time because unlikely things are going to take a long time to guess. So the average is dominated by these unlikely things in terms of the average until you guess the true thing, the true noise. But I don't actually care about the true noise. Basically, the Shannon typical set, the time by which you've guessed almost all the noise is here. Here's probably 0.99. What's going to happen is that I don't need to guess the true noise. I need to guess the true noise often enough that my probability of error is very small. In particular, I can just abandon. If I've been guessing for a long time, it basically means I got a funny noise, I'm just going to drop it because it's likely that my noise is wrong. Okay, so lots of math later, and I have backup slides if anybody's interested. Here it goes. If I look at the number of guesses until the random length and noise is identified, for very broad classes of noise with memory, so not interleaving, really taking the structure into account. And by the way, the more structure the noise has, like for instance, having a Markov model for the noise, the faster my decoding is and the higher my rate is. What I have is that this noise, this guessing function here satisfies a large deviation principle. And what we did is we used some results in LDPs from Ken and his student Mark Christensen. It has a rate function which is related to the Rényi entropy rate, 1/2 that I talked about before. The codeword difference noise is a minimum of 2 to the NR uniforms. It also satisfies an LDP. And the coding theorem says that the probability that I guess the noise before I guess one of these codeword difference noises is going to be such that I'm looking at the minimum of the two that will be satisfied as long as I am below capacity. What does that mean? Remember, I told you the brute force, which was the Shannon brute force. Here I have a binary symmetric channel, which is bit flips, I, D, 10 to the -3. Here it's Markov bursty. So, the channel actually has some correlation. I'm using the correlation, the knowledge of the statistics. What I'm going to have here is that the complexity goes up quite a bit. These are different code lengths, 100, 200, 300. The complexity goes up quite a bit because this is exponential, this is an exponential, this is a log scale, so this is an exponential growth. So you can see that if my code rate is even very low, like 0.2, 0.1 or whatever, my complexity in guessing, if I was doing this the brute force Shannon way, is out of control. If I guess the noise instead, it's flat. It doesn't really matter relative to the rate, except, and this is a little caveat to what I said before, except that when the rate gets high enough, actually, because I'm going to start making some more errors, but again, it's still the maximum likelihood, my complexity is going to go down. And the place here where I have this knee going down is actually the cutoff rate. Okay, so I am rate independent, except when I go down in complexity with rate. Okay. So as I mentioned, I can abandon. I don't need to code up to the very end. But I promised you at the beginning something better. I promised you at the beginning that I could do things that were not doable before. Remember, I showed you those BCH codes, those CRC-aided polar codes, and other codes, Reed Solomon, and I told you I can do better. I can do better than just, I can have something denser. I can do all those purple dots I told you about. Okay. This is the evolution of practical coding, as I showed you before. Remember, Shannon started random codes. Actually, I don't need random codes in general. Random linear suffices. Okay, and we know this since Gallagher, since the 60s/70s. Basically, just take a random matrix. That's as good as doing that random distribution. I told you, why is it important it's a matrix? Because a matrix is a really short description of a code. I just give you a matrix, right? It's just a matrix where I do a parity check. I see the code book. I see the code word. I put it in the matrix, and I can tell you right away whether it was a code word or not. My checking of whether what I received is actually in the code book or not takes no time. Okay, so storing the code word and the code book here and checking is super easy. All right, let's go back to what we did at the beginning of the talk, because I promised you that I could do better than the state of the art. Well, this is what I'm going to do. This is what those randomly new codes are. Remember, blue means lower rate, red means higher rate, of course, with concomitant increase in probability of error. I can have any code word I like. Any code word length I like. I can have any rate I like, anything I want. It's random, it's uniform, you just pick anything you want. And this is what's going to give me these purple dots. So these purple dots that were not possible before, right? Because remember, I had very few choices of length. In some cases, I had very few choices of rates. These purple dots means that I can do whatever I want. By the way, these are not random codes that were optimized. This is not like we search over multiple random codes. We picked the first code that we found. We just dipped into a hat and picked the first code. As a matter of fact, you can do this over and over again. Almost all codes are good, except the ones we know. Structured codes are bad, but you almost never fall in a structured code if you choose random. I told you about soft information with polar codes, but I didn't tell you what it is. Basically, soft information is not just knowing, well, I think I saw a 1, but it's giving you some information about what you actually observed at the physical layer. So it's giving you some more detailed information about the noise that you encountered. How am I going to use that soft information? At first, it would seem like you can't do that, Muriel. You're doing a guessing over a discrete set. Soft information is basically getting closer to the continuous world. How are you going to guess on a continuous space? But remember, I'm not really guessing the noise. I'm guessing the noise effect. That's why I've been really highlighting the noise effect. Okay. And here's a comparison where basically we just had a paper that just appeared at ICC 2020 with our student Mid Solomon. And this is with full soft information. It turns out that some very cute, very cute algorithmic issues that come out here, but I won't go into them. But I am happy to talk about them offline. Or you can also choose a very simple discretization of this floating information. This is with full soft information, with this discretized information. Again, remember, I don't really care about the noise itself. I just care about which effects are more likely than the other effects. That's all I care about. And that's what this is taking into account. This is an ordered bit reliability or grant. And I'll just show you a couple of results. This is with hard information only. This is with a CRC-aided Polo code. This is if I only had simple reliability. This is like a chase decoder for you guys in decoding. So I basically can just tell you this bit is reliable or not. That's it. This is 10 to the minus 1 probability. So basically 10 to the minus 2. So here basically I only care about having block error rate up to 10 to the minus 2 I abandon. That's why I get this floor. It's a design floor. I could get a floor lower if I wanted. This is the state of the art with full soft information. This is no soft information. This is very partial soft information. This is with full soft information. And this, the red one, and this is with this approximate soft information that I told you about, which requires far fewer bits. Some surprises, which I showed you at the beginning, sometimes I do better with just hard information and grant than I do with soft information and state-of-the-art decoders. And I do much better, of course, with grant with soft information. Here's the Polo code. Here's the random code. The random codes do at least as well as the Polo codes. So the Polo codes are good because they're getting me to basically the same as the random codes. But this is a random code. There's an infinite number of them, and there's no IP with those. This is pulling it all together if you want. Again, hard information, Polo codes with soft information. I've taken out the 1-bit information. Polo codes with that we decode, because remember we're universal decoders, so we're decoding Polo codes here with soft information, fully or approximately. Random linear code, they're all the same. These are all the same. And they're much better than state-of-the-art. By the way, state-of-the-art chips that we know about, which are the TSMC Huawei chips, actually use, this L here's the list size. It's basically giving me how well, it's giving me some indication of how well my decoding does in this list decoding. And as you can see, 16 is actually much better than what the state-of-the-art chips that we know about do. They actually do about 8. It's a single decoder. Here I have length 64, length 96, length 128. Again, remember I'm going from blue lower rate to red higher rate. The same decoder is decoding all of these for random linear codes. All of these. I can get all of the points I want. So that density that I showed you is a true density. I can, you give me the rate, you give me the length, bam, I decode it. So this is it. This is the new vision. Make the math work like the engineering. And I think I have a picture of, no, sorry. Here it is, the chip that we just sent out to tape out, which I hope to tell you more about. All right, very good, thank you. All right, so I see a few things in the Q&A. Yeah. Rahman, do you want to manage them or do you want me to just pick them up?
Yeah, so there are actually 3 questions. We have actually 2 minutes, but let's see how many we can answer. Sure. But first of all, thank you for the wonderful and thought-provoking talk. So the first question is that it seems that whether guessing the noise or the code would be SNR dependent. In high SNR, R is large and H of N is relatively low. Yeah. And it is easier to guess than noise. But in low SNR, R is low and H of N is larger relative to R. And it is easier to guess the code word, suggesting that the decoding strategy switches at a threshold SNR.
Yeah, absolutely. So you would have, if you had a very low SNR, then again, you would guess on the, if 2 to the NR was very small, then you could do that. So you're absolutely right. The only thing is, basically, that's not what happens in just about any system that's out there. But you're absolutely right. So if 2 to the NR was very small, so if you had a very small R, that's what you would do. But that's just not where systems are, but that's absolutely correct.
Okay. All right. Next question is from Ashu. So are there any downsides with random linear code, or more finely among random linear codes? Are some better than others?
So that's a good question. Originally, we thought there would be some that are better than others, But basically, we can't pick one that's bad. Again, you'd have to construct them bad, and the ones that are bad pretty much are just, the structured ones. So we really thought originally, we had even come up with this concept of code mining. We were going to mine for codes. You don't need to code mine. I mean, this is like surface mining. Anything you grab is good, which was a surprise to us. Very much a surprise to us.
Is there an intuition why, like having looked at them, why that really happens?
Yeah, so it happens because basically, they're really on what you want. So remember that the coding theorem is actually not based on distance, on minimum distance, the way that we're thinking of constructing codes. It's just based on sparsity. And so you'd have to be very unlucky to get them clumped. So it's actually a very, very robust aspect. As long as, you're more likely to get the noise than guess the code word difference noise. That's all that matters.
Yeah.
So sorry, this is Benham, Muriel. You mostly talked about the binary symmetric channels and such, right? Now, and then at the end, you mentioned something about, but I felt like continuous alphabet and it so-called AWGN channel. And now, is there a similar concept of guessing the noise in that case, or am I thinking in the wrong direction?
So the AWGN, thank you. That's a good question, Benham. So the AWGN was not a continuous alphabet. It's the noise is continuous.
Mm-hmm.
Right, but the input is still discrete. I mean, there are, all systems use discrete alphabets. All comm systems use discrete alphabets. So the noise is continuous.
Okay. Got it.
But we don't just do binary, So I was showing the BSC but you can do any sort of any amplitude, any modulation, and actually we've been doing quite a bit of work on modulation aware grant, which I didn't present. I only presented a small amount of the work, but that's a very good question.
Thank you.
Thanks. Raman, I think you're muted.
Sorry. So Edward, do you want to maybe ask the question, or should I read it? So Edward asked, do you have any thoughts on Grant's performance in Wi-Fi, especially if interference, hidden terminals, etc., could cause additional challenges?
That's a good question. So this is related to something that I mentioned early in the talk, but I didn't elaborate, but we are working on, which is basically having bursts of errors, right? So you have a bursty channel. So it turns out if you have a bursty channel, you can do much better than interleaving. So if you had a channel, even say something which caused all of your bits to be in error in a burst, you would not want to interleave. You would want to guess along those bursts, and that would actually give you quite a bit of benefit. So we haven't looked at we haven't done experiments on Wi-Fi. We sort of went directly to the chip for the reason that we wanted to, there's a lot of, by the way, I didn't go into it, but there's a lot of interesting aspects, really interesting aspects around the chip architecture, in particular, that the error generator is separate from checking the pertinence to the code book. But we actually believe that anything that's bursty, as you're mentioning, we don't believe. We have results. We have shown, not specifically for Wi-Fi, but that bursty will actually truly benefit from doing Grant. Does that answer your question, Edward?
Okay. Yeah, I'm not sure. So, yeah, actually, there are two more questions. I don't know if you have time.
Sure.
Okay, so the first one is from Yasaman. what noise statistics would yield to the upper bound performance of grand?
I'm not quite sure what you mean.
So Yasaman, would you like to follow up?
Yeah, sure. Yasaman here. Thanks for the great talk. So you mentioned the structured noise would give us some advantage for guessing its impact in grand, right? So I was wondering if there is some mathematical formulation of what structured noise is, what type
I see what you mean. Yeah, I get it. Thank you. Yeah, so basically, the lower the entropy of the noise, the easier it is to guess, right? Which means, you could have two noises with the same, so you could have two noises with, say, the same bit flip probability, but if one is more correlated, it's easier to guess. This is actually going back, I think, this is actually, in a way, similar in spirit to Edward's question, right? If you have bursty noise, it's easier to guess. And actually, if I go back to that picture that I showed you here, sorry, if I go back to this picture, see here, these two have the same bit flip probability, but this one is Markov. There's actually some correlation. It turns out this is easier to do than that. And the rate is correspondingly higher. Does that answer your question, Yasaman?
Yeah, yes, got it, thanks.
Yeah.
Okay, so last one. How do we know, which is from Chiai, how do we know which noise is more likely? How does the decoder adapt when the noise behavior changes?
Well, that's a great question. So, whatever you know about the noise, right? So if you have no clue and the whole thing is interleaved, you go back to Hamming distance, maybe sort of prioritizing, like I showed you in the example, which was very purposeful, that, you get more noise at the end, say, than at the beginning. But any statistics you can dump in there. So typically what happens is quite a bit about the noise statistics because you're measuring it as you go along, right? Any diffusion feedback equalizer is basically measuring what's going on in the channel. But we then don't really use that, okay? We use it very mildly. So anything you know about the noise you can use. And if you know nothing, you're back to, the status quo ante where you interleaved and just assumed it was uniform.
Okay, perfect.
Yeah. Okay, great.
All right. Thank you so much, Muriel. That was a fantastic talk.
Thank you.
And again, thank you for accepting our invitation. And hopefully, at some point, you could actually visit us at Rice.
I would love to do that. I would absolutely love to do that. And I hope by then I can show you the results from our chip. And by the way, our chip, we will be able to decode RLCs, we'll be able to decode Reed-Solomons, BCHs, and your favorite code.
Yeah, that would be fantastic. All right. And also thanks everyone for joining today. That's the end of our talk today. Hopefully see you next time.
Thanks, Muriel.
Thank you.
Thank you, Muriel.
Thanks, everyone.
Thanks, Muriel. Bye.
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 Bye.